This is a follow-up video from my last one on auxiliary controlled reactions. I'll just do a quick recap now because it's been a long time since my last video. Really sorry about that, everyone. Life just got really busy. I was looking at this specific reaction between an enol boronate and an aldehyde to form this new carbon-carbon bond, where I've started with a Z enolate, so this double bond is defined to have the Z geometry, and we have a stereocentre on the alpha prime site of this enolate equivalent. This whole unit is called a lactate auxiliary because it's derived from lactic acid, and we can use that stereocentre to very precisely induce the new stereocentres in the product. So what we can see here is that these methyl groups are set 1,3 anti, and because we had a Z enolate, we also get these two stereocentres in a 1,2 syn relationship. So overall, using a Zimmerman-Traxler type transition state, the Z enolate is leading to the 1,2 syn product, that's those two down stereocentres, but specifically the 1,2 syn down stereochemistry, not the 1,2 syn up stereochemistry. The Zimmerman-Traxler type transition state looks like this. Here we can see the purple aldehyde at the front, the aldehyde being activated by the enol boronate acting as a Lewis acid, and the lowest energy transition state for the aldol reaction is believed to go via this chair-like transition state, which is the lowest energy of the possible reactions. Note that these types of processes are under kinetic control. I explained in my last video why this is the specific transition state that we get, and it's largely due to the fact that the Z enolate geometry pops this hydrogen in this position on the transition state. It's known that if you have this geometry of a double bond next to a stereocentre, it's got reasonably free rotation around this bond. The lowest energy conformation for this system will project the dipole of the CO bond connected to the benzyl ether parallel to the CO bond of the enolate equivalent. This minimises the dipole interaction and favours this conformation. And so if we do the reaction at a cold enough temperature, this becomes the dominant route for the reaction and we get the product up there. Now this is all well and good, provided we want this 1,2 syn relationship in the product. The Z enolate will always lead to that one. If I wanted those two stereocentres pointing up, all I'd have to do is use a different enantiomer of starting material. But that begs the question of, what if we want the 1,2 anti relationship? And that's what this video is going to be about. So in the first instance, let's just try and tweak what we've got here. One thing that's not going to change in the Zimmerman-Traxler model is what we're doing with the groups on the aldehyde. We're always going to want this R' group equatorial. It's much bigger than the hydrogen on the aldehyde, so let's keep it in the same place going forwards. And now let's see what happens if I start changing things on the enolate. We'd expect this to impact the stereocentres in the product, specifically this one and this one with the orange arrows. Let's just take those out for the moment. Those stereocentres are determined by the enolate geometry, so I'm going to make a change from Z to E. We'll worry about how we do that later. I can make that change in the transition state as well. All I'm going to do is switch around the hydrogen and the methyl group. And now we run into our first issue. Because we have a stereocentre on the same side of that CC double bond as the methyl group, we have to use the Hauck model. And specifically, we need to minimize allylic strain in this situation. This is a form of restricted rotation. There will be one preferred conformation over all the others, and that's to minimize a steric interaction. The hydrogen here, highlighted in yellow, must eclipse the methyl group. The benzoxy group and the methyl group on that stereocentre are too big to do this. By doing a quick rotation around that bond, so that hops the hydrogen to where the benzoxy group is, the benzoxy to where the methyl group is, and the methyl group to where the hydrogen is. So now we've minimized the allylic strain, we have a much lower energy conformation for the starting material. There's nothing we can do about the enolate geometry. We've already decided that we wanted to use the E enolate. So you might notice that we're actually stuck here. We've ended up with a transition state with two biggish groups highlighted here in red, but it's not exactly clear whether it would be best to point the methyl group forward or the O-benzyl group forwards. They're pretty similar in size, so if we play with this transition state any further, we're not going to get anywhere. We'll still end up with two transition states of similar energy, which just means we'll get low diastereoselective ratio for the product. Not ideal. It turns out if we want to fix this, we're going to have to make some more modifications to our starting materials, but luckily there's quite a neat way of doing this. We can make this work by changing the benzyl group for a benzoyl group, as in have an ester rather than an ether, via the following plan. I've just deleted some bonds for us there to have a play around with, so let's see how this pans out. So as I said, my first change will be to change the benzyl ether to a benzoyl ester. So what I mean is doing this. Now that might seem quite a strange change to make. What are the consequences? The lone pair on this oxygen is no longer available. The lone pair is delocalized into the carbonyl group as part of the ester. Another thing that we've changed is that we've added another oxygen, which itself has lone pairs up there. And so we've sort of extended the chain just here. So there's an extra 2 atoms to another lone pair that wasn't there before. Well, how does that help the transition state? We've now got another lone pair that can actually do an internal hydrogen bond. Well, I mean this in a non-classical sense. If we have an activated aldehyde in our transition state, the carbon of said aldehyde is actually more delta plus than normal. So what we're saying is the effective nuclear charge of that carbon atom is a lot higher than normal, so that CH bond is more polar than normal, and so the aldehyde hydrogen, the so-called formyl hydrogen, has a delta plus charge. This can act as a lone pair acceptor. There's some dots for us. So if we have the benzyl ester group on our modified starting material on the front, we will be able to get this extra stabilising interaction, which will lower the transition state energy for this setup, and then we've got some differentiation that we can use to get diastereoselectivity in our product. Okay, let's build this in slowly. What we need is a lone pair here to encourage a formyl hydrogen bond. We can get that extra stabilising interaction if the ester group is coming forwards on our starting material. Perhaps we could draw it something like this. That would mean that the lowest energy transition state here would have the methyl group necessarily backwards. So this should be the lowest energy setup for us. The 3D is a bit tricky here, so feel free to pause and think about it. Just as a summary, we started off thinking about this activated aldehyde wanting to put its big R group, which is much bigger than the hydrogen, in an equatorial position. We also wanted an anti-aldol product, so we made sure we used the E-enolate geometry. So those two things are fixed. As a result of us having the E-enolate geometry, we have to put this hydrogen and this methyl group in yellow, eclipsing. This will minimize allylic strain. That is the lowest energy conformation by far for that molecule, so we're going to have to stick with that. And in doing so, one possible transition state allows us to coordinate an additional hydrogen bond by reaching that benzoyl ester across the middle of the transition state to interact with the more electron deficient hydrogen on the aldehyde. This non-classical hydrogen bond is enough to lower the transition state energy relative to the case when you don't have that, so that we can get diastereoselectivity. Right, let's translate that back into our starting material so we can see what we actually did overall. The ester group is normally abbreviated to BZ, so I'm just going to stick to that convention for benzoyl. And now using our more stable transition state, we can now work out what the stereochemistry is. Using this orange star, hopefully we can convince ourselves that we need that methyl group backwards to make sure that these are the same configuration. If it's easier to see it, remember of course that the hydrogen is forward as well. So now I've picked a very specific starting material with that auxiliary. That's not going to change during the reaction, so let's just pop it into the product. So our auxiliary has that specific stereochemistry. So what's that done to the rest of the molecule? Having a focus on the transition state, I'm going to have a look at this part highlighted in yellow as a sort of zigzag mapping onto this part of the product. We can see here that this methyl group is up relative to the hydrogen on the alpha carbon, so I can draw that into my product. It's the methyl group in front and the hydrogen below. And then for the final stereocentre, we can see that the hydrogen on the beta centre, the newly forming stereocentre, the oxygenated stereocentre, the hydrogen is up relative to the oxygen, so therefore the hydroxyl group in the product will be down. And so using this specific auxiliary, we can get this specific product in preference. Just making a quick note, we started off with the down methyl group as drawn on the auxiliary on the starting material. That translated to a 1,3 anti relationship between the methyl groups on the product, and because we had the E-enolate geometry, as expected, we've got the 1,2 anti relationship between the methyl group and the hydroxyl group across the newly forming stereocentre in the aldol product. So what I'm saying here is that we've managed to find a way to specifically get this combination of relative stereochemistry. We started off with the auxiliary with the methyl group down, and that will give us the exact product on the right hand side. If we wanted to, we could just change this around. If I started with a different enantiomer of the starting material, as in the auxiliary has the methyl group forwards, like this in red, that will still stay the same in the product because that's not where we were doing any bond forming. we would still get the 1,3 anti-relationship between the methyl groups. In this case, this new methyl group will be down on the alpha stereocentre, and the hydroxyl group will be 1,2 anti relative to that on the beta stereocentre, so that will be forwards. Note that these two compounds are enantiomers, which is what we should really expect, as the two enolate equivalents were enantiomers of each other. So as there are no other chiral reagents involved, these two reactions are exactly equivalent to each other. We've been able to find a way, by tweaking the auxiliary, to get both configurations of the anti-relative stereochemistry across the newly formed carbon-carbon bond. So for example, if we could find a way of completely getting rid of the auxiliary, we would never know it was there, and we can move on with our synthesis with our new centres in place. So there are two final things to address here. One, how did we form the enolate in the first place in the E geometry? And two, how do we get rid of the auxiliary in a useful way for forward synthesis? Okay, I've just cleared off some of the notes there so that I can give some more explanation around the edges of this reaction. Firstly, I want to know how we made that enolate geometry. This is our starting material, which we can make from lactic acid. And it turns out quite neatly that we can just use standard soft enolization conditions to do this. If I use cyclohexyl boron chloride and triethylamine, this would be a pretty standard way of making an E-enolate anyway. It will just work perfectly here as well. Now, I discussed this in my previous video, that when we had a benzyl ether around, it's a bit trickier when you form the enolate geometry because the oxygen lone pair on the starting material can also chelate to the boron. It would form a 5-membered chelate. But here, the oxygen lone pair is not available because it's conjugated. So we just got our standard explanation for why an E-enolate geometry will form here. I'll leave a reference in the description below, but the gist of it comes down to the following. I need to remove a hydrogen from that alpha proton when it's in a perpendicular conformation to the carbonyl like this, so that my sigma bond here can interact with the pi star on the carbonyl group. So to be able to form the enolate geometry, I need to make sure the molecular orbitals are overlapping first. The cyclohexyl boron chloride is quite a bulky Lewis acid. The chloride is not a great leaving group either, so the following complex forms, where the boron likes to sit near the front, where the boron sits on the same side as the ethyl group, rather than on the same side as the benzoyl ester. Just because it's much less hindered on this side, it's not branched, for example. Some computational work suggests that there's also some sort of interaction between this hydrogen and the chloride, sort of like another non-classical hydrogen bond, which further stabilises this conformation, although strictly the argument would be the same whether this was there or not. Just putting the remaining groups on here, there's a methyl group at the front. Exactly as we had before, we're going to try and want to keep big groups away from that. In fact, we can put the hydrogen into the eclipse position right now because we're about to form the enolate after deprotonation. And so the remaining groups will go on something like this, ready for our weak base to deprotonate and form it completely. I mentioned that some computational work had been done on this reaction from the mid-1990s. That work also showed that this isn't quite the right transition state in the middle. It turns out that with that internal formyl hydrogen bond, the lowest energy transition state is actually a boat type conformation rather than a chair, just by a little bit. But we might as well build that into our picture just for completeness sake. It doesn't change any of the outcome. It's just with this sort of bicyclic system, it's a better arrangement for the atoms sterically. So I can do that quite quickly by just tweaking my diagram. And now the 6-membered ring that we normally look at is in a boat-like conformation. But as you can see, it doesn't change the outcome of the reaction at all. So you might ask, why am I worried about this? Well, I wouldn't be for here, but this is just a simple version of this reaction. If I were to add more stereochemistry or have a slightly larger molecule doing this aldol reaction, it might turn out that there are other interactions that I need to consider that might compete with this core transition state. Okay, and then the next step in all of this would be, well, what do I do with that product? The auxiliary was only there to help us set up those new stereocentres. We don't necessarily want it in our final product, so what can we do? If I'm doing a complicated synthesis, I don't really want to carry around that beta hydroxy ketone. There is definitely an E1CB elimination risk with many types of forwards reactions. So probably the first thing you want to do after doing an aldol reaction like this is to protect the hydroxyl group. There are lots of things we could do here, but for the sake of something simple, I'm just going to put a silyl ether on there as a kind of default boring protecting group. And then let's turn our brains to how we might remove that auxiliary. I'll just clear up some space. There are many different things we could do here, but I just thought I'd show you some of the neater ones. Something you don't see all that often, but would be cool if you're on a small enough scale, is to react this protected aldol product with samarium diiodide in the presence of methanol. Samarium diiodide is a pretty cool reagent. I'll put a link to a review in the description. The main thing that it does is to act as a reducing agent. In fact, it's a single electron reducing agent. The samarium likes to go from oxidation state 2 to oxidation state 3 in most circumstances. This reaction overall just replaces the benzoyl oxy group for a hydrogen. Now it may not be obvious how that's working, so let's just have a look at the mechanism. We have an ester and a ketone on our molecule. They both have pi bonds in them, therefore the LUMO of this molecule is a pi star. The lowest energy of those pi stars is on the ketone. It's more electrophilic, it all follows together from that. So we expect it to be easier to reduce the ketone than the ester. So the samarium, I'm just going to draw it samarium 2 and ignore any ligands for clarity. That's what these square brackets mean. The samarium 2 is likely to associate with the oxygen lone pairs in the first instance, and then donate an electron into that pi star. In doing so, we've oxidized the samarium from samarium 2 to samarium 3. That leaves us with a radical on our molecule like this. Now, one thing that we can't do here is do an elimination such as this. Definitely not. This would break a standard organic chemistry rule for radicals. The CO bond is too strong to break homolytically like this. We can only homolytically break weak bonds, which is why we could do it with the pi bond at the start. So the radicals hanging around can't do an awful lot, but it is going to be floating around with some more samarium 2. It can just pick up another electron. It can be reduced further, is what I mean. So another samarium 2 can donate an electron, giving us samarium 3 and the anion, the negative charge, on the carbon that used to be the carbonyl. Now we're in the territory of being able to break bonds heterolytically. Elimination of this beta leaving group is perfectly fine. So we can do something standard with curly arrows like this. We'll get no control on stereochemistry there. There's no particularly strong lot before that elimination. If we inspect what we've formed here, we now have a samarium enolate. And as any metal enolate would do in the presence of methanol, it can just pick up a proton and get us to this ethyl ketone product. Pretty neat. So overall, we've just substituted the benzoyl oxy group for a hydrogen. Just for clarity, let's not draw in that terminal methyl group, and hopefully it's now more obvious that we can go off and do further reactions like this. Maybe even another aldol reaction if we carefully enolized it. Now that's all well and good burning out that group directly. We've sort of then incorporated some of the atoms from the auxiliary in our intended product. You could maybe say that calling it an auxiliary is not really strictly accurate there, but you'd only want to do this if you're on a small scale. You wouldn't want to be chucking out loads of samarium diiodide. On a large scale, that's going to get quite pricey. An alternative way of doing a similar transformation would be to first treat the reagent with ethyl magnesium bromide and have a careful think about what happens here. Again, we've got a ketone and an ester. The ketone should be more electrophilic than the ester with a nucleophile, such as this Grignard. But I'm going to propose that we're a bit sneaky here and we use at least 2 equivalents of this Grignard. Now, why would I want to do that? The first thing that's going to happen is that the ethyl magnesium bromide will attack the carbonyl in the standard way. Now, there might be some diastereoselectivity in that reduction, maybe due to the Felkin-Anh Model or something, but for our purposes, that's not going to matter, just worth a note in passing. If we have an excess of the Grignard, however, this ester group isn't going to survive that. And when we attack an ester with a Grignard, we'd expect it to react like this. In fact, let's just chuck in a massive excess of the Grignard just to make sure. And essentially what's happened in that first step is that we've completely cleaved off the benzoyl group. The observant among you will notice here that we've attacked an ester with a Grignard, so we're going to need at least 2 equivalents just to do this, because the product that we form first will have a ketone in it, which will then be more reactive than the ester itself. So we need at least 3 equivalents of the ethyl Grignard, in fact. And after an acidic workup, we'd expect to see this product, along with this byproduct that comes from the ester cleavage. We should be able to purify that away by column chromatography. The thing that I really want here is this diol. It's got the 2 hydroxyl groups here in a 1-2 relationship. Whenever we have those types of 1-2 diols, we can cleave the carbon-carbon bond between them using sodium periodate. That's this structure here. Just quickly redrawing for the mechanism there. Our diol will be a good bidentate ligand for that iodine 7 species. So the chelate effect will make us favour this complex formation. This can collapse to reduce the iodine 7 down to iodine 5. Which is a bit more stable for it. In doing this, we get to the same product that we had before. We could redraw that ethyl group, for example, to make that a bit more clear. So this route could well be better on scale. And note that the other thing we could do here would be we could vary that ethyl group. If we wanted to form a methyl ketone or some other type of ketone, we could just change the Grignard that we're going to use at this stage. There's one more cheeky manipulation that we can do here with this protected aldol product. So I'll just take a copy over to the left hand side. It's worth noting that rather than using a Grignard, we could just use a hydride reducing agent in a similar way. So let's just follow that through. I've got an ester and a ketone, so I want something that can reduce both of those. So let's think lithium borohydride maybe, and put that in excess. So this will be nucleophilic for the carbonyl of the ketone and the ester, and leave us with a diol a bit like we had before, except this time we've got a hydrogen directly attached to the carbon as indicated by that arrow. And then we can see what happens when we treat that with sodium peroxide instead. We'll do the same thing of chelating up the diol, but this time the oxidative cleavage will give us an aldehyde instead. Now that can be quite neat because, well, we can do more reactions with it. All is good. So for example, we could even do more aldol reactions using this as the aldehyde components. Now things might get a bit fiddly with this. You might note that that's no ordinary aldehyde. Both of those stereocentres will influence the diastereoselectivity of any reaction that attacks that carbonyl with a nucleophile, maybe by Felkin-Anh Model, maybe by an Evans polar model. But that's a much bigger story for another time. I've used these ideas in some of my other videos, and I'll link them in the description if you want to look them up. So my intention with this video was to do some awareness raising of a reaction type that might not be particularly familiar to many of you, but it's super useful in polyketide natural product synthesis, for example. I also just want to apologise for the big gap in releasing videos on this channel. There will be more coming soon, as I've now got more time to record the ones I want to do next. So stay tuned.